I'm happy to be here to see so many people I met before and part of my crowd. And so, of course, I want to acknowledge Chris of the big influence in my career, right? Guiding me first, as a graduate student. And people have already acknowledged, many of his ability. Actually, one point that I want to emphasize, maybe it was not done enough, actually, that one of the things I've learned from Chris that I thought was very important is actually that when you are a mathematician, you're often also part of a community, right? And so he encouraged me from the beginning to engage with people of my age and older people, people that he told me over the year would become my collaborators, my friends, and people I would, consider related to me. And so I remember going to Vienna, right, where at the time when I was a graduate student, Feitinger was setting up the NUAG. At the time, Karl-Heinz Gorking was not yet there, right? He was in the US and eventually joined the team. And of course, then I met my other relatives through John Benedetto. And in fact, this is a picture that I haven't seen yet being presented. I think this was for the 60th birthday of John. And I happened, exactly, yeah, it was 2 years ago, right? And you see, you couldn't recognize me, but I'm there, right? Anyway, I happened to be in a lucky spot. You see, I was kind of the center, and I see many people. My father, Chris, right? My grandfather, John, and also my great-grandfather in the background, right? That was there for the occasion. And you can see some of you. Denise Jacobs actually she was the second student of Chris. And perhaps at the time, perhaps Chris, that castle was not, I don't know if you were yet not yet a student or not there in the picture. But anyway, so this is actually how my family started. And actually, through this event, I met people. For example, I met Glenn, and we did some great work together. And I interact with many of the people there. And so it was actually nice to go along this journey for many years. I graduated in 2020, right? And so anyway. Okay, so my talk is a collaboration with my colleague, Robert Azenkot, Nicola Sharon, Andreas Mange, and my student, Jishi. This is about, as the title say, doing clustering on manifolds using some type of maps. And what is the connection with frames and the topics I discussed in this course? So while I was listening to the many interesting and insightful talk, one point that I see being a clear connection is this one, right? That nowadays people work with data, right? And when you work with data, there is a clear structure coming from their metric. So you can, whenever you work with data science, you can measure distances with this data, but data are not always, or often they are not naturally in a Euclidean space. So often you need to bring this metric structure into Euclidean space, and in Euclidean space, you can build frames and structure where you can understand data, right? But before doing that, sometimes you need to do something else. And my talk, in a way, is related to the topic of how you embed your data into metric structure, and how can you do that in such a way that will lead you to some efficient algorithmic machinery. And so the focus here on clustering. And what I like about clustering, it is one of those problems where it is very easy to state what the problem is, right? And you get a very good intuition and you expect to get some results. And the results that you see appear very believable. But however, anything you try to prove about clustering is always very hard, right? This is my experience. So let me first say what clustering means in a more theoretical, more rigorous setting, right? So we have a set of points, a finite point in a metric space. So V is the vector space, D is the distance, and I want to partition my data in such a way that, my points, where I fix the number of clusters. So I assume that I choose K, and I want to group my data in such a way that they are well separated, right? That they are, you group points according to their proximity in a certain sense. Now, the natural way to quantify this process is through the dispersion, right? If you have a set CL is my cluster here, the dispersion is the sum of the distances squared between the points and the cluster, right? This is for points in a cluster. This is going to give you a number. And so what cluster aims to do is you want to minimize what I call the total dispersion, which is, overall possible partition of size K. You want to find the partitioning that minimizes this sum, right? So clearly you see that there is a combinatorial flavor in that type of problem. So solving this problem in general is not going to be easy, but let me make an observation that maybe was assumed but not true, right? So everything I said so far is stated in a general metric sense, but when we think about clustering, we're naturally driven to think about the Euclidean setting. So in the Euclidean setting, of course, the dispersion is associated with an L2 distance, but the key point is actually that a centroid is nothing else than the arithmetic average, right? The arithmetic mean of the points. And we sometimes don't realize that the fact that a centroid in a metric in a Euclidean setting is computed so simply is something that doesn't carry over in general to other type of metric settings. So anyways, you're going to minimize total dispersion, you end up with an NPR problem. However, here you're making the problem in a way unnecessarily hard for most applications. So you know that there are efficient ways to in fact get high convergence, and the one of the most popular solutions still widely used is the k-means algorithm that has in fact some variants. The algorithm is usually associated with the Lloyd version of the algorithm, which goes back to 65 and works more or less as follows, right? This is the idea. It is quite simple. So you get a set of points, right? You choose k, the number of clusters you want to get, and you start by randomly selected some centroids, and then you repeat the following two steps, the assignment and update step, which means that you assign each point to the closest centroid. Once you do that, you artificially create some cluster that they're usually not optimal. Then you recalculate centroid by taking the means over the assigned points, and you repeat over and over, right? When you do this process, the centroid move until you end up in a configuration which is typically a local minimum, and so you get a partition. This works well. It is rapid to do, and it is rapid to do in the Euclidean setting, because when you work in Euclidean setting, you're just computing Euclidean distances, and centroid is just standard means. Now, think of carrying out the same process, not in an Euclidean setting, but in some manifold, right? Say a Riemannian manifold, so that we have a metric. So in this case, the distances that before were just L2 distances now should be, in general, geodesic distances, which may be fine. Sometimes those can be expressed in a closed form. But usually the most difficult step is actually to compute in the centroid, because the centroid now is not just the arithmetic mean, right? You need to, in fact, solve an optimization problem, which is giving you what is called the Karcher mean, sometimes also called the Frechet mean, which means that you want to minimize, right? Find the y, minimizing the sum, right? And this can be solved usually numerically, iteratively with regradient descent, which of course is in general more expensive than just doing what you do in the Euclidean sense. Now, here just a fact, because I said that this is what you should do, but of course, in general, you're not really guaranteed that such minimum exists. And just mention a fact that, in fact, if you work in the set of simply connected, complete Riemannian manifold with non-positive section curvature, then this quantity is guaranteed to exist and is unique. This is the setting which I will consider. And this is the setting that includes, for example, an important class of data, which are those associated with the group of symmetric positive definite matrices, which is the one where I will focus the most, which is important. But in general, this property is true for what is called the Cartan-Hadamard manifold, which are exactly the manifold for which the property I stated is true, right? So simply connected, complete Riemannian manifold with non-positive section curvature. And so the curvature is important to guarantee convergence, right? And so why I care about this problem? So one motivation comes from medical imaging. When you work in neuroimaging, you take measurements over time, for example, via MRI and fMRI. And in this case, SPD matrices computed from this data are a way to measure the strength of neural connection between brain sites. And so doing clustering is a way to, in fact, try to infer potential connectivity patterns and things of this sort. There are other applications for SPD, but this is a primary one. And what is important about this problem is that SPD matrices in this case can be quite large, right? So working the complexity numerical, computational effort increases in this case if you work with SPDN or large size. So a few words about SPD, right? This is, I mean, I'm sure quite known, but just a brief review for mostly for notation here, right? So SPD matrices are symmetric positive definite matrices, as in the definition. They include the Hilbert matrices with entries of this form, right? The most important example are the non-singular correlation matrices and covariant matrices. If you take n vectors, right, and you compute the covariance between any pairs, you can define this covariance matrix, and then you can, in fact, get the correlation matrix by applying this sort of standardization, assuming that the diagonals are non-zero. There is an additional example, which is actually not proper, but so mutual information matrices is also used a lot in applications. So if you check the literature, you see that they are not guaranteed to be SPD. In fact, there are examples of mutual information matrices which are not SPD, but in fact, in practice, try to compute an MI matrix for any data, you will always find them to be to satisfy the SPD condition. So in a way, those are closely related to SPD matrices. Now, just to emphasize, they are not a Euclidean space, right? So it is not a vector subspace of Euclidean space. For example, if you take averages, right, of SPD matrices, the result is not an SPD matrix in general, and a known phenomenon. I mean, I don't need to convince you they're not a Euclidean space, but there is this phenomenon which is interesting and shows actually that if you average them, you get this sort of swelling effect, right? So anyway, you cannot compute the average of a set of SPD matrices just as you do with Euclidean points. Now, of course, you can apply multiple matrices, multiple metrics in SPD. The special one is the affine invariant Riemannian matrix, which is defined here, right? And under this matrix, which is a geodesic distance, so under this distance, which is a geodesic distance, the SPD is a Riemannian manifold. And in fact, we'll make SPDN as a manifold of dimension n by n plus 1 divided by 2, right? Because you see the entries are symmetric, so the dimensionality is not n squared, right? It's a little less than n squared. Okay, now let me go to now the key point, which is actually clustering by Frechet map. And this is the idea, right? The idea that I presented at the beginning. When you work with data that are just in a metric space and you want to carry out some analysis, right? You know, only having distances may not be enough, right? So the idea actually that I present here is actually using what we call a clustering by Frechet map, which means that we introduce a map which is taking points from SPDN. We can do this, in fact, for a larger set of Riemannian manifold, the Cartan-Adara manifold I mentioned. But anyway, the idea is to define a map that takes these points into a Euclidean space, hopefully of small dimension, with the property that distances are almost preserved, right? And now if I'm in a Euclidean setting, at this point, my analysis is easier. I can, if you want, you can use your frames and any representation system which is convenient for you, and will make the analysis easier, right? Now, what is a Frechet map? So there is a family of Frechet map we call P-Frechet map, which is constructed this way. The idea is kind of elementary, and I try to give you some intuition. So this is defined on any metric space, right? Doesn't have to be a Riemannian manifold, any metric space. So you take a set of points in the manifold, right, or in this vector space, and with respect to this point, you compute distances, and so this way you map any point from the metric space into a vector in RL, right, where those are the distances between your query point and this L coordinates, right, the way I took, right? So this way you go from the metric space into a point, in fact, in the positive real, right? Now, you can do this for any P. The idea of P1 goes back to a paper by Bourgain. The other interesting case is the two Frechet map, which is differentiable, while the other map is only Lipschitz, right? And here a brief historical note. Bourgain has this celebrated paper, 1985, which is establishing, in fact, that for any finite metric spaces, you can embed this space into a Hilbert space with a relatively controllable distortion, right? So this is in the spirit of other theorems or results that have been used frequently in dimensionality reduction, like somebody of you may know the Johnson-Lindenstrauss lemma, which also states some embedding between two metric spaces, right? But in the JL lemma, in fact, is for Euclidean space. So the Bourgain work is remarkable because it works for any metric space, while the Johnson-Lindenstrauss lemma is also only true for Euclidean metrics. The other point which is different is actually the Johnson-Lindenstrauss lemma does this mapping through a linear projection, while Bourgain can be nonlinear, right? And so the proofs rely, in fact, on probabilistic technique. So the Frechet map is an example of such a map, which is explicit, right? And so what we've been trying to do is to understand what is this map doing. So we have evidence that we present at in the second part of the talk about the fact that this is in fact useful. So we saw that it works. But here I want to show, try to understand what this map really does in terms of mapping points from a metric space into a Euclidean space. So first of all, why is this useful for us, right? And so let me specifically look at the clustering problem. And the idea is very simply, I take the k-means approach, and what I'm doing in two words is actually, before doing I take my points in the manifold, I map them to the Euclidean space, carry out the clustering in Euclidean space, and then go back, right? And this doesn't even need to get the inverse, because you see, I take my points, XR are my points in SPDN, right? I fix some, I call it reference point, gamma 1, gamma L. I will go back to this selection of these points later. And now I compute my coordinates, right, in the Euclidean space, apply k-means, and to go back, I do not even need to compute the inverse, because my points are labeled, right? I can relabel them. So this is a way to avoid computing car-share means and only doing a clustering in the Euclidean setting. Of course, you need to compute these distances right there, which will require some cost. So what is the point of this? The significance, as I said, actually, that you can carry out the most intense computational intensive step of the clustering, which is computing the car-share mean in the Euclidean space. And I can quantify the difference because what I need to do in this Frechet map setting, I need to compute n times L distances, where L is the number of reference points and n is the number of points. This computation will require little n cube computation, where n is the, okay, here maybe I go to, n is associated with the dimension, right, of the space, right? If I, on the other end, right, do this using the computing directly car-share mean, the order of computation is n to the 5. So the difference is between this L and cube and n5, right? So this becomes much more efficient if I can keep my L small, right? This is the point. Now, what about the property? What is this Frechet map doing, right? And what can we understand about the geometry of this map, right? We said that we were trying to build this map in such a way that is actually almost isometric, right, or close to be isometric. And so when p equals 1, one can prove it. This is relatively simple, that the map is globally Lipschitz. When p is larger or equal than 1 is only locally Lipschitz. More generally, right, in fact, if you work on a manifold, you can also show that for p larger or equal than 2, this is also differentiable, right, which is a property that may be useful. Now, to get an understanding of what it does, I mean, we started by looking at the situation, which is not practical, but useful to see what happens if I apply a Frechet map from a Euclidean space to another Euclidean space, right? I want to understand what type of distortion is actually applied, right? And so this is done with, by working with real numbers, right? So I take two balls in R3, right? I take 3 reference points, and you see between any point in the ball, I compute the distances, right? So I map any point there to another point with respect to the new coordinate associated with R1, R2, R3. And here I show what happens through a 2 Frechet map and a 1 Frechet map. So what you see here actually that, what this suggests is that balls are mapped to sets which are not necessarily balls, but are still disjoint, right? The map is, as he said, is Lipschitz, right? Or local Lipschitz in this case. And so the intuition is actually that, in fact, this map does preserve injectivity, right? We can guarantee, in fact, that by choosing the number of reference point sufficiently large, right? This is what the theory. This is actually the first theoretical result. This is valid for Frechet map between Euclidean space, right? So if I take my number of Frechet points to be here is large, right? Because the map is from Rm, right, into RL. If my L is largely equal than m plus 1, which is therefore a lot, right? In this case, I can guarantee that the map, in fact, is diffeomorphic. If L is equal to m, although in this case I get essentially injectivity, right? Injectivity also holds on an appropriate half space. So we are, in both cases, we have local invertibility. So we can, in fact, guarantee, that the map in this sense is well behaved. But here is one point, right? So if I want to achieve clustering, so separation of the cluster, right? It is not sufficient to get injectivity. You also want the two sets which are separated in the original domain are still separable by an hyperplane in the map space, right? And so you want to guarantee some type of convexity. And we can prove that the convexity holds, right, if you take the two Frechet map, but doesn't hold for the one Frechet map in general, right, in this very generic set, right? Now, the theory that we've been able to work through so far, is limited, but you see, in the sense we're asking a lot here because, I'm working under trying to establish a result by choosing my reference point in a very generic manner, right? So what you think that in practice, right, if you want to build this type of map, you're looking for reference point which special property that in fact achieve the special property you desire. So the heuristic observation that we have, we're not yet a theory for that, is actually that we can build convexity preserving map by choosing the reference point appropriately, right? So this is what the picture was suggesting. That so if you essentially you're going from Euclidean space to Euclidean space, by choosing your points in a certain way, you can apply some sort of nonlinear change of coordinates where you can make your data maybe similar, right? Or at least convexity preserved. Anyway, so here so far, I've only been looking at the, try to understand the Frechet map from Euclidean space to Euclidean space. So already in this setting, there are some theoretical questions which are open. In practice, we care about what we can do, not just going from Rm to RL, but on a generic Cartan-Hadamard manifold, for example, on SPDN. And so let me tell you what we know about SPDN, right? So also in SPDN, we can show the local invertibility is true, right? In the sense that actually, again, if we choose our reference point to be many, so of the same order equal to the dimension of the space, then we can get local invertibility. But again, so this is in line with what we saw in the Euclidean setting, however, a little far from what we want to achieve in practice, where we want to get the number of reference points smaller than the dimension of the manifold, right? So there are open questions here. We know heuristically the idea works. So there are some interesting mathematical questions that eventually, essentially pertain to understanding the type of geometry, right, of the manifold, and how this type of map is in fact distorting the data. So the last part of the talk is about what in fact we can achieve through this machinery. So, before, going very deep into the theory, we want to, at least this was our strategy, to verify that this idea works in practice, right? And we in fact do have some evidence, and I will give you a brief summary of what we tried so far. And so in terms of theoretical analysis, right, at the moment, we can only guarantee, the desirable property of convexity preserving when we choose the number of reference point large. But in practice, we found that this number, in fact, can be taken small. Obviously, the performance will depend on the choice of these points, how you place them, right? But we found a heuristic strategy that is computationally fast, cluster agnostic, and consistent in performance. Right? I made at some point a comment, but yes, here I made a comment. Sorry, I forgot to because I added this one after listening to some talk, maybe the one by Ursula, that she mentioned about the issue of the related to intrinsic dimensionality. So you see. Morally, right, you expect that the number of reference points should be of the order of the true dimensionality of the problem, right? If you want to separate two clusters which are well separated, essentially this is a one-dimensional problem, right? And so the true dimensionality is not the embedding space. It's not where your data live, but what is the true information content of your data, right? And so L morally should go of that size, right? And this is what we find in practice, right? So what is the idea, right? Now, all the synthetic example you see will be done with balls, right? And of course, because I'm trying to do clustering within the k-means setting, this is the type of data you're typically are able to deal with, right? If you ever work with clustering, you know that k-means expect your data to be more or less balls or not too far from that, right? If you take data which are very long and elongated, k-means fail, and so inevitably this will also fail. So all my examples, synthetic example, will be of this type. Now, what's the idea, right? So let's suppose that I have my data aggregate around two balls, and I want to place my reference point in such a way that when I build this map, the map will preserve this type of distance, right? And so intuitively, what you want to do is if the two balls are close, you will place your reference point inside, right? If they're far away, you place your reference point inside. So the distance is there will discriminate the two data. And if they're close, you want to place them outside, right? Now, in principle, would be only sufficient to choose one in the middle and one outside, but this become unstable. So we decided to take two inside, either two inside or two outside, depending on how they are, right? Now, this is the idea, right? And still you say, yes, but you can place your reference point in that location, right? If you already have an idea about how they look like, right? And in fact, you can use some intermediate step to try to guess more or less where they are, right? And you can do this, for example, using the log Euclidean map to estimate the approximate locations in order to fix the reference point. Now, there is another strategy which is totally agnostic, which is I can place my point randomly. It works rather well, right? But this is actually more efficient, right? So I say, to place my reference points, I need to estimate the location of the centroid. And for that, we can use the log Euclidean framework, which means that you essentially approximate locally the manifold with the tangent plane. Of course, this may already give you a good clustering, but we found that in fact it doesn't work, is kind of inaccurate. We have example to show the case. So once we use the log Euclidean framework, then we can locate our reference point and carry out the type of clustering, right? So we run multiple numerical experiments along this idea, right? By looking at balls in SPD of similar sizes, not the same, random location, multiple dimensions, so even high dimensions, to test the idea. And we compare with other techniques. One is the so-called, we call intrinsic Riemannian clustering, which means that this is the direct approach where you compute k-means by doing the clustering with the geodesic distance and the Karcher mean. There is an accelerated approach, which is, we call it iterative Bayesian clustering. Some people propose this idea, which is actually speeding up this approach. And so those are the two main methods which are available. And so we compare this on multiple data sets. Here, for example, we work in SPD 20. This is a large dimensional space. It's 20 times 21 divided by 2, the dimension of the space. And so our results are highly accurate. In fact, they're more accurate. This is mostly due to, I think, numerical errors coming out from the other technique. But we get a speed up, which is significant, with respect to IRC, 14 times, and 8 times with respect to the other technique. Now, if you compare with the log Euclidean clustering, right? I said that you can also approximate, right, your the distance using the log Euclidean map. And we show in several examples. Here, for example, we randomly generated 250 version of 4 balls in SPD4, and we compare, right, our method. This is the 1 map, this is the 2 map with local Euclidean map. And we find that specifically the 1 map is way more accurate, right? Of course, we run multiple draws, and so the standard deviation may be rather large, but definitely we gain in accuracy with respect to log Euclidean sets. So we also try with some data which are kind of experimental, with texture data, with some of the neuroimaging data. And also let me mention that we did not only use this idea with clustering. You can also apply this idea to problem like classification, right? For example, you can use KNN, which is a way to classify data based on nearest neighbor idea. And if you try to do KNN in the manifold setting, you can also apply this type of map, and this will give you a significant speed up. By the way, in that case, your map doesn't need to be injective. So in that case, you do not even care about anyway. So the requirement of the dimension of the reference point is even reduced in the type of set, right? Anyway, that's all I wanted to tell you. So that's all, and so thank you for attention, and happy birthday, Chris.